Parametric equations are really useful for seeing equations in a new way and hopefully being able to manipulate them in a way that you couldn't if you kept them in their normal form. So what we do with a parametric equation is when we are given a function or equation, something like y equals x plus 3 to the power of 5, we introduce a new variable. Sometimes we call it u, v. Most commonly in parametric equations, though, we use either t or theta. And normally they represent different types of parametric equations as well, so you have different rules depending on which variable you've been introduced to. But you should have seen a parameter before, so this new variable t, in C3 when we were doing the chain rule. So in the chain rule you would introduce a new parameter, say t, to equal x plus 3. And this would then allow you to differentiate. So we would set y is equal to t cubed, where t is equal to x plus 3. You'd then be able to differentiate each part of those and then use the fact that dy by dx was dy by dt multiplied by dt by dx. So without even knowing it, this sort of seemingly big and slightly scary thing of parametric equations you've actually been using since C3. Skill you need to have when it comes to parametric equations is being able to convert parametric equation into a Cartesian equation. And there are two methods for doing this. Usually when the parameter is t, you're talking about just functions, little equations and stuff. Things that aren't involving logs or trig or anything like that. They're just linear or quadratic or cubic equations. Usually when you're using theta, you're talking about trig. And so this is normally another method or another approach you can use to getting those two equations to work. So when you have a parameter of t, normally the easiest thing is to set one equation to t equals and substitute in. So for instance, in this case, we can say that on this equation here, t is equal to x minus 2. So y is equal to x minus 2 squared minus 3, which is obviously a quadratic in the completed square form, but we can expand that out. So that's x squared minus 4x plus 4 minus 3. So y is x squared minus 4x plus 1. When you have the parameter of theta, normally you need to use a trig identity. So something like the fact that sine squared plus cos squared is 1, and that will help you sort of merge these two parametric equations back into one Cartesian equation. So, for instance, in this example, x divided by 3 is sine theta, and y divided by 4 is cos theta. So if I square both sides of that equation, I've got that x minus 3 squared is sine squared theta, and y over 4 all squared is cos squared theta. Now I know that sine squared theta plus cos squared theta is 1, so x over 3 all squared plus y over 4 all squared must be equal to sine squared theta plus cos squared theta, which is 1. So that's gotten rid of our parametric variable theta and left us with an expression that we could obviously multiply out and everything as just in terms of x and y. And if you expand this out, you'd get an x squared term and a y squared term, which means we're talking about circles, which is quite nice because you start to see circles as rather than these kind of big scary things with x squareds and y squareds and how on earth do you manipulate that kind of algebra, as parametric equations with just sine and cos. So here's an example question. The topic is in coordinate geometry. So you're going to be looking at points of intersection, meeting the x-axis, the y-axis, other curves. Sometimes those curves will be in parametric form as well, so you'll have to be comparing two parametric equations, or they will be in Cartesian form, so you'll either have to convert your parametric equation into Cartesian form, or use it in parametric form, but be looking at it as an intersection with a Cartesian line. So in part I, we want to know whether the curve meets the x-axis, or the point where it meets the x-axis. So we know that any curve equation line function meets the x-axis where y is 0. So obviously we can't use that x is 2 plus t at this point because we haven't got a y to make equal to 0, but we can use the other half. So we know that the curve meets the x-axis where y is 0, so we are interested in this equation. So we know we're actually going to find values of t at this point, and that's fine. We know that t squared is equal to 3, so t must be plus or minus root 3. So the points where the curve meets the x-axis are 0 minus root 3 and 0 plus root 3. Those are the 2 points where that curve meets the x-axis. In part 2, we're interested in the point of intersection on that curve. So we're looking for where that curve meets the other curve. So we're looking for a coordinate or a set of coordinates where that's the case. So we know something about x and y, but in terms of this new parameter t. So what I would be doing is just substituting in our expressions of x and y for our parametric curve straight into this new equation, because actually we know something about y equals, we know something about x equals, but we just know it in terms of t. That's fine, it doesn't have to phase us. So if y is 2x plus 1, and that's the other curve we're interested in, let's substitute in y equals t squared minus 3, so we've got t squared minus 3, equals 2 lots of 2 plus t, which is x, plus 1. So now we've just got, hopefully, an equation in t that we can manipulate to give us values of t. So I've just multiplied out that bracket, so t squared minus 2t minus 9 is 0. Take that over, that's minus 4, take that over is minus 5. 8. Teaches me for doing maths late at night. Okay, so I can factorise that, I hope. T and t, we want minus 4 and plus 2. And that's equal to 0. So we know that t must be 4 or minus 2. So if we want points of intersection, we're interested in Cartesian coordinates. So values of t is useful, but it's not going to help us particularly. But we now have two values of t that we can substitute into our equations of y and x to give us the x and y values that correspond to these points of intersection. Make sure though, if you're dealing with t is 4, you don't suddenly switch to substituting in t is minus 2 into the other equation. So for instance, I'll just do one of them. T is 4. That's all we're interested in at the moment. So we know that y is equal to 4 squared, which is 16, minus 3, which is 13, and x is 2 plus 4, which is 6. So this t is 4 produces a coordinate 6, 13. And then this t is minus 2 produces, well, y is minus 2 squared, which is 4 minus 3, which is 1. And x is 2 plus t, so 2 minus 2, which is 0. So the other point of intersection is 0, 1. Just be clear though, curves might not intersect. So if you're given these two parametric equations of curves, or lines, you're wanting to find values of t gained from comparing the two x equations to the two y equations that match. So for instance, if you find values of t, and I'm just literally plucking these out of my head, that t is 4 and minus 3, for say comparing the x coordinate, the x expressions, but then find that t is 47 and 21 with the y expressions, then these two curves don't intersect. For them to intersect, you'd need to have the same expressions, same values of t, to be able to say that those two curves intersect. So that's just a warning. In the next video, we're going to have a look at how parametric equations helps us with integration. But do make sure that all of this is really comfortable for you, so that you're not being slowed down by just getting kind of a bit confused about parametric equations. So make sure this stuff is really good before you move on to the next video.